In the grand, silent gallery of the cosmos, planets have long been considered the spherical masterpieces of gravity. From the marble-like blue of Earth to the banded majesty of Jupiter, our conception of a planet has been inextricably linked to the sphere. It is a shape born of equilibrium, a geometric inevitability where mass pulls equally in all directions, smoothing out mountains and filling in valleys until a world settles into a hydrostatic roundness. But the universe, in its infinite capacity for surprise, has revealed a rebellion against this symmetry. Deep in the constellation of Hercules, some 1,800 light-years from where you sit listening to this, lies a world that defies the spherical standard. It is a world stretched, pulled, and tortured by gravity into a form that resembles not a marble, but a rugby ball, or, more colloquially, a lemon. This is WASP 103b, a gas giant that has become the protagonist of one of the most compelling detective stories in modern astrophysics. Dubbed the Citrine Anomaly by some for its spectral glow and its citrus-like geometry, this exoplanet offers more than just a visual oddity. It is a laboratory of extreme physics, a place where the polite tug-of-war of gravity we experience in our solar system becomes a violent, structural wrestling match. For the first time in history, astronomers have detected the tidal deformation of a planet outside our solar system. This is not merely a measurement of size or mass. It is a measurement of shape, and through that shape, a measurement of the very soul of the planet, its internal rigidity, its density distribution, and its potential fate. To understand WASP 103b, we must first understand the lineage from which it hails. The WASP in its name stands for Wide-Angle Search for Planets, a ground-based consortium that has been one of the most prolific hunters of gas giants in the history of astronomy. WASP 103b was first catalogued in 2014, identified as a hot Jupiter, a class of exoplanets with masses similar to Jupiter but orbital periods of less than 10 days. But WASP 103b was extreme, even among this extreme class. It is an ultra-short period planet, whipping around its star in less than a single Earth day, approximately 22 hours. The host star, WASP 103, is an F-type main-sequence star, hotter, larger, and more luminous than our Sun. The proximity of the planet to this blazing inferno is terrifying to contemplate. While Earth sits a comfortable 150 million kilometers from the Sun, WASP 103b orbits at a distance of less than 3 million kilometers. To put this in perspective, if WASP 103b were in our solar system, it would be orbiting inside the corona of the Sun, skimming the surface of the star with a speed that defies imagination. For years, WASP 103b was just another data point in the growing catalog of hot Jupiters. We knew its mass was about 1.5 times that of Jupiter, and its radius almost twice that of Jupiter. We knew it was hot, likely glowing with a thermal emission of over 2,500 Kelvin. But the true nature of its geometry remained hidden in the noise of ground-based observations. The breakthrough came with the launch of CHEOPS, the Characterizing Exoplanet Satellite, a European Space Agency mission dedicated not to finding new planets, but to studying known ones with unprecedented precision. Unlike Kepler or TESS, which stare at thousands of stars to find new dips, CHEOPS is a sniper. It points at a single star and stares with an unblinking, photometrically stable eye. In 2020, a team of astronomers led by Susanna Barros trained CHEOPS on WASP 103. They observed 12 separate transits of the planet. By combining this high-fidelity data with archival observations from the Hubble Space Telescope and the Spitzer Space Telescope, they achieved a signal-to-noise ratio that allowed them to see the shape of the transit curve in minute detail. A spherical planet produces a specific U-shaped dip in light as it crosses the star. But a deformed planet, one that is elongated at the equator, produces a subtly different signature. Its projected area changes slightly as it rotates and moves across the stellar disk. The team looked for these minute deviations, and they found them. The data favored a deformed ellipsoidal shape over a spherical one, with a statistical confidence of 3 sigma. The planet was not round. It was a rugby ball. It was a cosmic lemon. Why is WASP 103b shaped like this? The answer lies in the fundamental force of gravity, specifically the differential force we call tides. We are familiar with tides on Earth. The Moon's gravity pulls harder on the side of Earth facing it than on the center of Earth, and harder on the center than on the far side. This differential pull stretches the Earth slightly. On WASP 103b, this effect is magnified by a factor of trillions. The planet is so close to its massive star that the gravitational pull on the day side is significantly stronger than the pull on the night side. This colossal gradient creates a stretching force that overcomes the planet's own self-gravity, the force trying to pull it into a sphere. The planet is effectively being spaghettified, though not to the point of destruction yet. It is held in a state of hydrostatic equilibrium, where the outward pressure of its hot gas and the inward pull of its gravity are balanced by the stretching force of the star. To quantify this deformation, astrophysicists use a dimensionless parameter with a surprisingly poetic name, the Love number. Named after the mathematician Augustus Love, who first described them in 1909 to model Earth's elasticity, Love numbers measure the rigidity of a planetary body and its susceptibility to tidal deformation. Imagine a planet made of diamond or solid iron that refuses to deform no matter how hard you pull on it. That planet would have a Love number of 0. Conversely, a perfect fluid body, a homogeneous ball of gas with no central concentration of mass, would deform instantly and maximally, giving it a Love number of 1.5. Real planets fall somewhere in between. A planet with a massive, dense core like Earth will have a lower Love number because the mass is concentrated in the center, making the outer layers harder to pull into a bulge. For Jupiter, the Love number is approximately 0.59. This value tells us about Jupiter's internal structure. It has a core, but it is largely a fluid body. For WASP 103b, the CHEOPS team measured a Love number of 1.59, plus or minus 0.5. This result is staggering. While the error bars are large, the central value suggests that WASP 103b is extremely deformable. It behaves almost like a perfect fluid, perhaps even more so than Jupiter. This high Love number implies that WASP 103b might have a relatively small core compared to its total size, or that its internal atmosphere is so inflated and hot that it behaves with extreme fluidity. Knowing the Love number allows us to do something akin to an MRI scan of the planet from 1,800 light-years away. It tells us that despite having 1.5 times the mass of Jupiter, WASP 103b is not just a denser version of our neighbor, it is inflated, puffed up by the intense heat of its star to a radius nearly twice that of Jupiter. To appreciate the precarity of the Citrine Anomaly, we must introduce the concept of the Roche limit. The Roche limit is the theoretical distance from a star within which a second body, held together only by its own gravity, will disintegrate. Inside this limit, the tidal forces pulling the planet apart are stronger than the gravitational forces holding it together. WASP 103b orbits at a distance that is less than 20% larger than its Roche limit. It is dancing on the edge of a volcano. If it were to move just slightly closer, the star would win the tug of war. The planet would cease to be a planet. Mass would stream off its surface like a river, forming an accretion disk around the star before eventually being consumed. This proximity is what gives WASP 103b its shape. The surface of the planet is nearly coincident with its Roche lobe, a teardrop-shaped region of space around the planet where the planet's gravity dominates. Comparative planetology gives us a grim forecast for worlds in this position. WASP 12b, another famous hot Jupiter, is known to be spiraling inward. Observations have confirmed that WASP 12b is losing mass, and its orbit is decaying by about 29 milliseconds per year. It is a dying world. Astronomers expected WASP 103b to follow the same tragic script. With such extreme tidal deformation, the friction generated inside the planet should be dissipating orbital energy rapidly, robbing the planet of angular momentum and causing it to spiral inward. But when the team analyzed the transit timing data for WASP 103b, they found something shocking. In a plot twist worthy of a sci-fi novel, the data from CHEOPS, combined with older data, did not show orbital decay. It showed the opposite. The orbital period of WASP 103b appears to be increasing. This means the planet is drifting away from its star. In our solar system, tidal forces cause the moon to drift away from Earth at a rate of about 3.8 centimeters per year. This happens because Earth rotates faster than the moon orbits. However, for a hot Jupiter like WASP 103b, this mechanism should NT work. The planet orbits in 22 hours, while the star rotates much more slowly. In this configuration, the tidal bulge on the star should lag behind the planet, creating a drag that slows the planet down and drops it into a lower orbit. So why is the Citrine Anomaly drifting away? Astronomers have proposed three main theories. The leading non-gravitational theory is the Applegate effect. This effect links orbital changes to the magnetic activity cycle of the host star. As a star goes through its magnetic cycle, the distribution of angular momentum within the star's interior shifts. Layers of the star may speed up or slow down, changing the star's gravitational shape. This subtle change in the star's gravitational field can periodically alter the orbit of a close-in planet. If the Applegate effect is the cause, the widening of the orbit is likely temporary. Over a decade or two, as the star's magnetic cycle turns, the period might start decreasing again. The second possibility is the presence of a third body in the system, another star or a massive planet on a wider orbit. The gravity of this hidden companion could be tugging on the center of mass of the system, causing the transit times to vary. The third possibility is simply that science is a discipline of skepticism. The detection of the period increase is statistically significant, but it relies on data stretched over a relatively short baseline. It is possible that what looks like a trend is just noise, though given the precision of CHEOPS, this explanation is becoming less likely. Let us now imagine hovering in the cloud tops of WASP 103b. What would it be like? Hellish is an understatement. The day side of WASP 103b is tidally locked, permanently facing the star. Temperatures here soar to over 2,500 Kelvin. This is hotter than the melting point of most metals. Iron would exist as a vapor in the upper atmosphere. On the night side, temperatures are cooler, but still blistering. The heat distribution depends heavily on the atmospheric circulation. On spherical hot Jupiters, we observe super-rotating jets, equatorial winds that scream around the planet at speeds of up to 7,000 kilometers per hour. But WASP 103b is not a sphere. Its rugby-ball shape introduces complex new variables. The varying radius of curvature means the effective gravity changes as you travel from the pole to the equator. The bulge facing the star acts like a gravitational mountain. Winds trying to cross from the day side to the night side have to climb this geopotential hill, which could disrupt the super-rotating jets, potentially causing strange stationary waves or localized eddies. Furthermore, the deformation creates a phenomenon known as gravity darkening. Because the planet is elongated, the poles are closer to the center of mass than the tips of the rugby ball. Therefore, the poles should be hotter and brighter, while the distended equator should be cooler and dimmer, adding a thermal stripes effect to the planet. And the color? The name citrine implies a yellow hue. At 2,500 Kelvin, WASP 103b is radiating its own light, behaving like a dim star. The thermal emission spectrum peaks in the infrared, but bleeds into the visible red and orange. Combined with the potential for silicate clouds or titanium oxide gas, the visual appearance of the planet to a human eye would likely be a glowing ember orange or deep yellow, a terrifying bloated gemstone hanging in the void. To fully understand this anomaly, we must compare it to its siblings. WASP 12b is the closest analog, a dying brother spiraling into its star, darker than asphalt. WASP 121b is a heavy metal world, also football-shaped, where it rains liquid rubies on the night side. But our Jupiter, the control group, is a frozen spherical marvel. The fact that WASP 103b has a similar love number to Jupiter suggests that, despite the extreme heat and radiation, the fundamental equation of state inside WASP 103b is not radically different from Jupiter. It is still a gas giant, just one living in a blast furnace. The detection of WASP 103b's shape is just the beginning. The Citrine Anomaly has been flagged as a priority target for the James Webb Space Telescope. JWST will allow astronomers to refine the love number by measuring the phase curve of the planet with higher precision, telling us definitively if the planet has a large core or is coreless. It will also map the atmosphere, detecting the spectral fingerprints of water, carbon monoxide, and perhaps exotic species like gaseous titanium. Beyond JWST, the European Space Agency's Plato mission will monitor the orbital period over years, confirming whether the orbit is truly widening. The Citrine Anomaly teaches us a humbling lesson about the universe. We often think of planets as solid, immutable objects, static stages upon which history plays out. But WASP 103b reveals that planets are dynamic, fluid things. They are drops of water held together by the fragile tension of gravity, easily molded by the hands of their parent stars. This lemon-shaped world serves as a bridge between the study of planets and the study of stars. It blurs the line between a rigid body and a fluid stream. It challenges our understanding of tidal dynamics, showing us that even at the edge of destruction, a planet can defy the expected spiral into oblivion. As we continue to stare into the constellation of Hercules, measuring the minute dimming of a distant star, we are not just mapping the galaxy. We are testing the limits of physics itself, watching how matter behaves when it is stretched to its breaking point, glowing like a hot coal in the dark, refusing, for now, to be round.